transmission of random process through LTI filter. LTI means linear time invariant filter. LTI filter the transfer function or impulse response. Transfer function means in the frequency domain, h of t means impulse response in the time domain. So in the time domain, the response of the system, the characteristics of the system is defined with respect to h of t. That means impulse response of the system or the transfer function in the time domain. So for this system, I am giving random process as a input. Okay, I am giving random process as a input, say x of t. On the output side, I am getting some other random process, say y of t. Output side, I am getting some other random process. Now, what are all the properties of this random process? Okay, what is the properties of x of t in general before giving to LTI system? Then the LTI output, I will be getting some new output depending on h of t. Then anyway, definitely I will get some new signal, okay, new values. But what are all the properties? Whether properties are remaining same or not. Properties in the sense, I will calculate what is the mean here. I will also calculate what is the mean here, variance here. What is the property, statistical parameter? Okay, whether the statistical parameter remains constant or it is varying. So that is the main observation here. So usually, if you pass a random process through LTI system, the main observation is if this process is stationary in general, if this process is stationary, okay, in general, random process can be anything. It may be stationary or it may be WSS also, or it may be ergodic random process. But what we are trying to say, if that random process is a stationary random process, okay, already we know that what is a stationary random process. That means all the statistical parameter has to remain same. That means independent of time. If the particular process is a stationary random process, then definitely at the output also we'll get some other random process that is also a stationary. Okay, already proof is there in the communication theory. Already proof is there for this. Okay, once if you pass a random process through LTI filter, again if the input is stationary, output is also a stationary random process. This is one of the main observation. And then what about that power spectral density and other things? Okay. So usually that y of t is x of t convolved with h of t, impulse response. In time domain, we'll do the convolution, or otherwise, if you are writing in the frequency domain, say y of omega is equal to x of omega multiplied with h of omega. Already we know that convolution will become multiplication. Okay, convolution in one domain will become multiplication in the other domain. So in time domain, if you are having convolution, definitely in the frequency domain, we will have multiplication. Again, you have to be very careful with that 1 by 2 pi. Whenever we are using f instead of omega, sometimes we may get that extra constant, that is 1 by 2 pi. You have to be very careful. Or otherwise, when we are writing in the reverse, that means sometime convolution may be present in the frequency domain, then we may write multiplication in the time domain. So that time we may get extra 1 by 2 pi also. So you have to be very careful. But here there is no extra 2 pi here in this case. Okay, so we have defined y of t both in time domain as well as in the frequency domain. Okay, time domain means you have to do the convolution, frequency domain means just multiplication. Then the another observation here is output power spectral density. Okay, at the output we are having y of t. It is some signal, it will have some power spectral density. It will have some power spectral density. The output power spectral density is h of omega whole square. H of omega means for h of t we have to take the Fourier transform, that is h of omega. H of omega. Okay, so you have to do the square of h of omega because h of omega will be in the amplitude domain. But once if you are talking about the power domain, we have to do the square. So that's why h of w whole square multiplied with the input power spectral density multiplied with the input power spectral density. So output power spectral density is equal to system transfer function square into the input power spectral density. So in terms of notation, Sy of f, this is the output power spectral density, which is equal to system transfer function square than input power spectral density, say of f. Then how to calculate the output power, final output power? So output power is equal to integration of output power spectral density then df over the bandwidth. Okay, again you will be defining this function over some bandwidth, so that's why integration is with respect to the bandwidth. So that means starting frequency and the ending frequency, then power spectral density, output power spectral density, then directly it will give the output power. So mostly examல இந்த லாஸ்ட் 2 ஸ்லைட்ஸை பேஸ் பண்ணி கொஸ்டின்ஸ் வந்து அதிகமாக வரும். எதர் டைரக்ட்லி இட் மே பி ஃப்ரம் கம்யூனிகேஷன் சிஸ்டம் ஆர் ஃப்ரம் சம் அதர் சப்ஜெக்ட் கண்ட்ரோல் சிஸ்டம் ஆர் அதர்வைஸ் ஃப்ரம் மேத்தமெட்டிக்ஸ் ஆல்சோ கேட்கலாம். ஸோ இல்லைன்னா சிக்னல் சிஸ்டத்துலேருந்து கூட கொஷின் வரும். ஸோ இது எல்லாமே வந்து காமன் ஃபார்முலா தான் எல்லாத்துக்குமே இது. ஸோ இதை பேஸ் பண்ணியும் கொஷின் வரும். ஸோ இந்த லாஸ்ட் 10 minutes வில் சி தி ப்ராப்பர்ட்டிஸ் ஆஃப் ஒயிட் நாய்ஸ். ஏற்கனவே நிறைய டைப்ஸ் ஆஃப் நாய்ஸ் இருக்குது, but mostly we will use random noise and white noise, okay, for introducing noise in our system for analysis purpose. Mainly we will use thermal noise, okay, thermal noise or white noise. Almost the explanation of thermal noise and white noise is almost same, okay, with a little different. Okay, so now quickly we will see about the noise, thermal noise and white noise. I think that is given in the syllabus. Okay, quickly we'll refer the syllabus.